Here we break down the notation of a function into its two parts, the function itself and the argument. The function is the operator and is basically a simple set of instructions that will be carried out on whatever is input into it. We can imagine a function with no input at all, and it would look something like this, with the bracket showing where an input would go. This is a key point often ignored. The function can exist without any input. As for the argument, this is simply what we are choosing to put into the function at a given occasion. This can be a variable or a numerical number, and most certainly does not need to be x. It can be any letter or any number. F can also be any letter for that matter, and you will often see things like g of y or h of z or f of 2. All the variations can be separated into two parts, the function and the argument. Here I run through a simple example. Notice how the variable arguments on the left-hand side usually result in algebraic expressions, whereas if we use a numerical argument, as on the right-hand side, we usually get numerical answers. Next we move on to graphs, and it's useful to drop any prior knowledge of graphs and their uses because really the only use of graphs is to visualize functions, and any other description of them should have been taught as secondary. Consider the function g of x is equal to 4x cubed plus 2. What can we find out about this function? A reasonable attempt would be to make a table like this, pick some inputs and see what we get out. Here we gain 5 useful bits of information and find the outputs of these values to be minus 30, minus 2, 2, 6, and 34. It is clear that this tells us extremely close to nothing at all useful about the function. What if we wanted to know the output of 0.1 instead of 0? Or we wanted to see what the function would do to prime numbers if they were the input? This is where the graph comes in. The aim of the graph is to visually represent all the information about a function. To do this, we make a set of xy axes and allow our function to fill up some space on this graph. Here is the graph of g of x. For every possible input, which is the x-coordinate, there is an output, the y-coordinate, and a graph shows this relationship between the two visually. Unlike the table, once we draw the perfect graph, it contains all the information of the function. This curve is the function. Every point on it satisfies the condition that if you input the x-coordinate into g of x, what you will get out will be the y-coordinate. Take time to understand this and then notice the power of graphs. The visual aspect allows us to see the shape and features of the function, the type of characteristics you might not even think existed if you just looked at a table of numbers. The final key definitions in this topic are domain and range, simple but a potential banana skin. Each function has its own domain and its own range. The domain is simply the set of allowed numbers that can be put into the function. Allowed meaning it doesn't try something mathematically impossible. Similarly, the range is all the values that can come out of a function. The point is best illustrated with graphs and two simple examples. For the function f of x is equal to sine x, we can put any input we like into it, but we will never get an output that isn't between minus 1 and 1, which is clear from the graph. Therefore, we say that the domain of x is all numbers, and the range is that fx must be between minus 1 and 1. For the function f of x is equal to 1 over x, we see that we can put all x values in except x equals 0. It makes no mathematical sense if we try to make x equals 0. The result is undefined since you can't divide by 0, and so we state that the domain is x equals all numbers except x equals 0. Likewise, we can obtain any answer as the output of 1 over x except for 0. In other words, there is no possible input to f of x that would make the output 0. And so we state that the range of f of x is all possible numbers except f of x is equal to 0.